addresses many of the concerns that have been raised in the recent years concerning HHO, or hydrogen oxygen production, as it is applied to the internal combustion engine. Claims have been made that the introduction of the hydrogen oxygen mixture into the air charge of an internal combustion engine increases its efficiency due to the increased flame propagation speed, promotes a more complete and total combustion of the air-fuel charge within the cylinder. Up until recently, it has been very difficult to find supporting scientific, peer-reviewed, published data that supports the claims and the observations that have been made by HHO supporters, builders, and designers. Claims that include ones that have been made by myself. I have posted data, runtime tests, that demonstrate the viability of HHO as implementation into the internal combustion engine to reduce the amount of fuel consumption and emissions of that device. I ran multiple generator tests on a stationary Genset application that clearly demonstrated and was clearly documented savings in fuel consumption. The attacks that have been made are that there is no scientific, peer-reviewed, published supporting data. It has come to my attention that university tests have been done, peer-reviewed, and published in the scientific community that support the claims that I have been making, that support the viability of HHO injection technology. What you are looking at is page 1 of a document published in a peer-reviewed and accepted scientific journal. This test was run in Australia by S. Barry and M. Mohammed Esmail at the Sustainable Energy Center, School of Advanced Manufacturing and Mechanical Engineering, University of South Australia. This document is a peer-reviewed university scientific study on the viability, examining claims of HHO injection into the internal combustion engine. And much to my happiness, much to my excitement, this test was done on a stationary generator, diesel-powered nonetheless, which of course interests me greatly because, as I have recently announced, the focus of my company is being directed not on vehicles but on stationary generator applications, which ultimately will be used in vehicles as onboard charging systems for series hybrid electric vehicle applications. So this study is part of my supporting evidence that I am presenting to the skeptical community that HHO injection does in fact work. Here is the first page of that study, published and accepted on the 21st of August 2009. As I said, published by Elsevier in Fuel magazine, and you can see the credentials of this publication at their journal homepage listed at the top of the document, www.elsevier.com, locate fuel. In the abstract, the results are discussed and clearly stated as the following. Results show that by using 4.84%, 6.06%, and 6.12% total diesel equivalent of H2O2 mixture, the brake thermal efficiency increased from 32% to 34.6%, 32.9% to 35.8%, and 34.7% to 36.3% at 19 kilowatts, 22 kilowatts, and 28 kilowatts respectively. These resulted in 15.07%, 15.16%, and 14.96% fuel savings. It also says the emissions of hydrocarbons, CO2, and CO decreased, whereas the NOx emissions increase. And I will address the NOx emissions results later in this video. First, let's go over the experimental apparatus, the test apparatus. A dynometer was used on the engine and loaded under a variety of load conditions between 2 kilograms and 10 kilograms. Compared to diesel, and this is one of the claims that I've made and I want to elaborate on. Published in this journal, it states, compared to diesel, hydrogen has wider flammability limits, higher flame speed, and faster burning velocity, which enables engines to run on very lean mixtures. Go to my Genset videos that are posted here and see and witness for yourself the data sheet, the data spread that shows that this statement, which is being made in this scientifically published, peer-reviewed university study, that correlates with this statement. On the second page of this paper, it goes into discussing some of the properties and characteristics of hydrogen. But part 2, it goes on to explain the experimental setups and procedures. It says a Hino 40WD 4-cylinder direct injection and water-cooled diesel engine was used in this experiment. The detail of the engine is listed in Table 1, where, as you can see, all of the different parameters of this engine are indeed listed. The mixture of hydrogen-oxygen was generated by electrolyzing water using an oxy-hydrogen generator machine, Epoch EP-500. In order to simplify the setup, the H2O2 mixture was generated using 24 volts of external power. Now, this is a statement that may cause many of the skeptics to raise up in unison to say the test is invalid. However, reading carefully the document, which I know that you will, says, in reality, it will be produced from the battery/alternator arrangement of the engine. The power needed to produce the H2O2 mixture is included as input energy to the engine. That means that even though the cell was not directly connected to the output power of the generator, it was included in the final calculations. Therefore, the system can be viewed as a quote-unquote closed system with no external power based on those calculations. On this statement published in a peer-reviewed scientific journal, a study done by an accredited university. One point of contention that I do have, there's actually 2 points of contention that I have. The first one is listed in part 2. It explains the gas measuring device. A Dwyer model RMC gas flow meter was used to measure the H2O2 mixture flow rate flowing into the engine with an accuracy of plus or minus 0.5 liters per minute. The only concern that I have is these gas flow meters that are being used aren't necessarily, in my opinion, accurate to measure the correct flow rate of the hydrogen-oxygen gas mixture. That is because this does not take into account the different density of the hydrogen-oxygen mixture. I am not completely familiar with the Dwyer model RMC gas flow meter that was used. If it was not properly calibrated for hydrogen-oxygen gas mixture in that proper 2/3 ratio, the volume may be of question. That is the only item of contention that I have. The third page of this published, peer-reviewed scientific journal performed by an accredited university again states, the flame speed of hydrogen is 9 times faster than the flame speed of diesel. This is a claim that I have been making and a statement that I have been making ever since I first started endorsing the use of HHO boosting and building boosters and informing the public of the viability of this technology. It goes on to say, Therefore, burning diesel in the presence of hydrogen will result in overall faster and more complete combustion. Again, a statement published in a peer-reviewed scientific journal. If you look at the top of the page, you will see the experimental setup block diagram, which clearly explains how the system was arranged. Below that, for the different kilowatt load ratings, you see two graphs. One is a variation of brake thermal efficiency with H2O2 percentage, and it goes from 0% to 7%. You can see the delta inefficiency as the amount of hydrogen is increased. Same thing on the right hand side, figure 3, except you're using flow rate instead of percentage, from 0 to 35 liters per minute. Now notice the 35 liters per minute is a lot of gas. Most of the designs that are out there that are being built, replicated, sold are not over 10 liters a minute. As a matter of fact, the average is about 2 liters a minute. But even so, on the graph between 0 and 5 liters per minute, you can see a very definite increase in percentage between those two flow rates. These two graphs clearly demonstrate that the addition of hydrogen and oxygen increases the brake thermal efficiency of this particular diesel application. And the page goes on to discuss, now this is very important, discuss tuning aspects, for example, port injection timing, okay, of that particular diesel engine. I bring attention to this fact because I want to reiterate the importance of tuning your specific application to the percentage of fuel used. If you're using HHO injection, you need to specifically tune your engine for the presence of that gas. I cannot emphasize that fact enough. And I have proven that. In my Genset, my own personal Genset tests that I ran, I proved that tuning was necessary. Adjusting the air-fuel ratio mixture was necessary. And I didn't even go into adjusting the timing. These guys adjusted timing to further increase, which would indicate a reason why every application may exhibit different percentages in increase. You may look at the graph and say, well, it took 10 liters a minute just to get a simple, couple percent increase in mileage. And that is because of the tuning. Tuning must be properly done. So again, I cannot emphasize enough the importance of proper tuning. That is why many times when people try to implement HHO technology on their vehicles, they may not see a gain or they may see a decrease in mileage. Without proper tuning, as I've demonstrated very clearly, the HHO injection method does not work. And that was seen in the Eric Krieg tests, combined with bad cell technology. When you design a cell that doesn't hold up, that falls apart, and you don't do proper tuning, you will not see results. Now, page 4 of this published scientific investigation on HHO technologies states very clearly, the figure reveals, and that's referring to figure 4 at the middle of the page, that the addition of a small amount of hydrogen-oxygen into the air intake to enhance diesel combustion decreases the brake-specific fuel consumption regardless of the level of the load. And in figure 4, you see 3 different load rates of 19 kilowatts, 22 kilowatts, 28 kilowatts. Each curve in brake-specific fuel consumption decreases. Figure 5, which shows the variation of total fuel flow rate with hydrogen-oxygen percentage, also shows a very prominent decrease in flow rate. Again, this is a scientific, published, peer-reviewed paper done by an accredited university. Figure 6 shows variation of fuel saving with hydrogen-oxygen percentage. In percentages, for each load rate, the observer can clearly see the increase in fuel savings as the hydrogen-oxygen percentage increases. Notice at about 5% in figure 6, the line seems to level off. This, according to the paper, indicates that beyond 5% induction, H2O2 mixture acts as a fuel rather than an additive. Yes, HHO is a fuel, and the more you add, the more you must tune, because the more it begins to overtake the role as a primary fuel source for the engine. Variation of air-fuel ratio with equivalent hydrogen-oxygen percentages. As the percentage of HHO increases for every power range, you see a definite increase in air-fuel ratio. Scientific public paper published, peer-reviewed, accredited university. Second to last page, we discuss the emissions. Clearly being shown, at 19 kilowatts, the hydrocarbon emissions drop from 187 ppm to 85 ppm with 31.75 liters per minute induction of hydrogen and oxygen. At 22 kilowatts and 28 kilowatts, the hydrocarbons emissions decreased from 189 ppm to 93 ppm by adding 29.84 liter per minute, and from 192 parts per million to 97 parts per million by adding 30.6 liters a minute of hydrogen and oxygen respectively. Again, these flow rates of hydrogen and oxygen are very high. Most cells are not producing that much gas, which would explain why the percentages are much smaller than published in this paper. For example, my device has never gone above a 20% reduction in fuel consumption, also done on small gasoline engines. You cannot apply the same percentage numbers on all engines ever made, burning on any different kinds of fuels. You're talking about apples and oranges. So one device on one engine will not perform the same as the same device on another engine. This is just common sense scientific principles we're talking about. You cannot expect to put a 2 liter per minute hydrogen generator on a big diesel engine and a 2 liter per minute hydrogen engine on a small gasoline engine and expect to see the same exact results. It is irrational to assume that all percentages are going to be equal across the board on every application. Specific tuning must be done, and the cell output should be designed for the engine that is going to be applied to. That being said, figure 8, variation of hydrocarbon emissions with H2O2 percentage. Clearly, showing as percentage increases, hydrocarbons in parts per million decrease. Peer-reviewed scientific journal, published, accredited university. Figure 9. This is one item of contention that I have. I'm not arguing with the data. Clearly shows that NOx rises with an increase in percentage of H2O2. And as I have discussed, NOx is the worst emission. The point of contention I have is that this data is not 100% conclusive because, as I clearly demonstrated with my Genset videos, if you lower the exhaust gas temperature, you can reduce your NOx emissions by virtue of the fact that NOx is formed due to high combustion temperatures of 2400 degrees Fahrenheit and above. That is also a known and published fact. Therefore, I propose that to deal with the NOx increase, that an individual can use water fogging to cool the combustion temperature, or can adjust air-fuel ratios to reduce combustion temperatures. There are a multitude of methods that can be used to cool down the combustion temperature to lower these NOx emissions. I did not see in this study where that was addressed. So, in my further research on my own, I will be addressing keeping the combustion temperatures low to keep NOx emissions low. Figure 10, the variation of CO2 with hydrogen-oxygen percentage clearly shows the same thing as the hydrocarbons graph. Same with the CO, all reduced. This paper concludes, hydrogen, which has about 9 times higher flame speed than diesel, has the ability to enhance overall combustion, generating higher peak pressure closer to top dead center, resulting in more work. Power equals energy over time. Everything that I have been telling you guys from day one. Watch Free Energy over Unity and why HHO works. I exactly, specifically address the issue of timing, of power, and energy. I have posted this thousands of times on the internet. I have argued over and over again. These are the concepts that cause HHO to be a viable technology that works. I'm going to read the statement again. A scientific study done by an accredited university, peer-reviewed and published in a scientific journal. Hydrogen, which has about 9 times higher flame speed than diesel, has the ability to enhance overall combustion, generating higher peak pressure closer to top dead center, resulting in more work. This peer-reviewed, publicly published scientific study is in direct conflict with personal accusations and claims made by individuals who are not peer-reviewed, who have not published a scientific paper in an accredited journal by a reputable university, using grossly insufficient BTU calculations to try and prove that hydrogen injection doesn't work, using a simple, rudimentary, Neanderthalic BTU calculation method. This paper, this peer-reviewed, published scientific paper, goes against those personal claims made through insufficient, inadequate calculations that HHO does work. Until there is a peer-reviewed scientific study done by an accredited university that can show that HHO injection does not work, I am going to take this peer-reviewed, published scientific journal done by a study from an accredited university. I'm going to take their word for it, and I'm going to continue with my HHO research in stationary gensets to be applied to electric vehicles with onboard charging systems. This is a viable technology, it's proven, and therefore there is no reason why it should not be pursued further. And that is exactly what I intend to do. No amount of skepticism, false BTU calculations, or accusations will be able to stop this valid moral research that is desperately needed to be done for the betterment of all mankind. I intend to do that no matter what the opposition, and I intend to continue to add more supporting evidence as it becomes available. This paper was brought to my attention by Jake, who has a master's degree in engineering. And he has posted some videos about this document and some other documents that he has found, and he is doing a thesis on HHO injection. So I want to give my appreciation and thanks to Jake for contributing to the HHO community and doing very scientific analysis on this technology and bringing to our attention these very important studies that back up what we have seen in real-world testing. Thank you for watching. Awake on my airplane, awake on my airplane. My skin is bare, my skin is theirs. I feel like a newborn, and I feel like a newborn. Awake on my airplane, awake on my airplane. I feel so real. In this video, I'm going to describe in full detail
the protocol and the methods and the equipment used. The reason why I've done these tests is because of the controversy and the skeptical, negative, naysaying mindset that has seemed to permeate the attempts of HHO researchers and the HHO industry. HHO technology works. HHO is a viable fuel. That it does combust, it does burn, and it does increase the combustion efficiency of an internal combustion engine. To prove with numbers and results, carefully measured observations, that not only is HHO a viable fuel, but it also does, as claimed, increase the fuel efficiency of the internal combustion engine. And I believe the best way to do that is to run these tests on a stationary genset with a given load. One of the primary objections is the objectiveness of the tests. The environmental conditions can vary fuel consumption, temperature, humidity, road conditions, road grades, the time of day, whether your windows are up or down, what your tire pressure is, when's the last time you changed your oil, your air filter, and most importantly, number one, is your driving style, habits, and traffic conditions. Now these are reasonable objections because all of those factors can and do affect fuel mileage, which make objective road testing very difficult. Now, those of you who follow my videos know that I run the same course at the same time of day using cruise control at the same speed. So I try to negate all those variable factors as much as possible, but there's still room for question, okay? Especially when you're only posting increases like I have of like between 7 and 16%. Those are very small increases relative to other factors that can cause deltas in fuel consumption. So I wanted to go to the stationary genset where no one can say, oh, it's a dirty air filter, because guess what, I took the air filter off. Or it's varying road conditions. Well, there is no road. There are no conditions. Where the temperature is relatively constant, the humidity is relatively constant, the load is definitely constant as measured with a load meter. Okay? You can't say it was driving conditions. You can't say it's tire pressure. You can't say it's operator variances, because guess what? The genset uses a governor. And that governor is set, and there it is. It runs at a specific RPM. You can't say that it's user interface. So I've attempted to, and I believe successfully, remove some of the most important variable factors in some of these fuel consumption tests. One of the first things is a scale right here. I am accurate within a couple seconds on this thing. I mean, it's pretty good. It's not absolutely 100% perfect, but it's good enough for this. I used a digital scale. That's the first thing that I wanted to show you, was the addition of a scale, okay, to measure the weight of the fuel that was consumed. 5.20 ounces is what came out on the scale, and I measured it multiple times. Now, the next addition I want to talk about is my load board. So I have 3 100-watt light bulbs, obviously an on-off switch, and they're all wired up in parallel, so they see the same voltage. Okay, nothing fancy there. Okay, and they're plugged into my kilowatt meter, which is able to measure the wattage consumption, and also the battery charger is connected through this adapter here into the kilowatt meter, and then the whole deal is plugged in, as I showed in the videos, right into the back of the generator. Okay, so all the power for the load and the cell comes from the generator. Okay, you need a standard load. I'm going to talk about that in a minute, but you need a base load. You can't just compare free spinning power consumption to cell consumption without having a load. You're replicating a constant driving experience. That's what this represents, and this never changes. I mean, the light bulbs, the resistance of the light bulbs don't change significantly. This is 300-watt load, and it's solid. It's consistent. Okay? Right there is a fuel adjustment mixture screw. okay, which allows me to change the air-fuel ratio with a twist of a screw. Being able to adjust your air-fuel ratio is absolutely essential to the success of the application of this technology. If you cannot adjust your air-fuel ratio, I'm telling you right now, and I'm about to show you with the data, you're not going to see jack for a change. You may get lower, you're going to get lower emissions, and I'm going to prove that with my data in just a few minutes. Same deal with the HHO injection. I've already gone over this before, so I'm not going to go over it in too much detail other than to tell you that I use the Gen 5 cell, again, which is more efficient than the Smackzilla cell that I use. Okay, and then the last thing I want to discuss about is the existence of this battery. Now, some people are justified in questioning the presence of the battery and saying that the battery is providing power to the cell. Now, I want to tell you, first of all, this setup is almost exactly like what's going on your car. So that would be like saying, well, I'm hooking an HHO generator up to my battery on my car, and the power to run the HHO is coming all from the battery, and so it's not really, I'm just draining my battery, and my battery will be dead at the end of my trip. And of course, you know, if you have a healthy battery and a healthy alternator, that's not what's happening. What's happening is the alternator is keeping the battery topped off and providing the energy necessary to power the HHO generator. This is a stationary vehicle. That's all this really is, okay? But to ensure, okay, to demonstrate that that is not the case, that I am not tapping power out of the battery to augment hydroxy gas production, is I have an amp meter, okay, which is connected to the cell, okay, showing how many amps the cell is drawing. And then I also have a meter on the battery charger. The battery has to be here because if it's not, if I just try to connect these clamps up to the cell, the battery charger won't work, it won't turn on. So when I plug the cell in, the cell draws all its power from the battery charger, and the battery charger is turned on because of the presence of the battery. All the power required by the cell is coming from the generator, period. Okay, and like I said, that was verified using my amp meters and also my kilowatt meter, because when I hook the cell up, I can see the kilowatt meter jump up to the expected watts. I mean, I've got my current, I know my voltage. Okay, so I expect the watt meter to increase by a certain number of watts, and lo and behold, it increases by the expected number of watts. That's the equipment. And of course, you know the generator, it's 11 horsepower Briggs & Stratton, and it's a 6300 watt generator attached to it. time to go over the data. Okay, so this would be the first test that I ran, Genset test number 1 and number 2. And the purpose of this first test was that hydroxy is a viable fuel, that it does aid in the combustion process of the internal combustion engine. What I want to show you is something that's missing. You don't see any exhaust temperature readings here. I didn't do any. I didn't do any fuel mixture adjustments. I didn't do any timing adjustments. Nothing. Completely stock. And also what I didn't do is I didn't put a dummy load on. All I did was use the generator, the hydrogen generator, as a load, and then introduce the hydroxy output tube into the engine, or not introduce it into the engine at different flow rates. Okay, and what I demonstrated was a 20% gain and fuel efficiency between putting the hose in the carburetor and letting it vent to atmosphere. Now that doesn't prove that HHO, when running in a closed, quote unquote, because I don't really believe in closed systems, but quote unquote closed system, does not prove that it increases your fuel efficiency, that it decreases your fuel consumption. What it does prove is that it is a fuel, it does combust, and it does make a difference in the combustion chamber and in the burn process. A couple of people noted, and correctly noted, that the difference between free spinning with no load and running with a load, that there was like a 15% decrease in fuel consumption. Okay, what I want to point out is that the efficiency of an internal combustion engine changes under load. In other words, with no load on it, okay, no load, you're just spinning components. You're not creating any you're not using any power. It's more efficient. It's going to run longer. No load. Okay? So, and then when you put a load on it, of course, it's less efficient. Your runtime is going to decrease. I wasn't trying to compare free spinning consumption with load consumption. I was just trying to demonstrate the fact that there is an increase in efficiency when you present the hydrogen, the HHO, into the engine. And I demonstrated that successfully. With these I averaged out my fuel consumption, and you can see that through the different runs, I did get an increased delta in each run. That was the purpose of the first set of tests. As you can see, what I do is I run blocks of 3 data points. What happens here is I choose a condition, a certain load, and I run 3 tests and I average the results. And what that does is for each block of test data, it kind of gives me a more accurate reading. It's like when you're doing mileage tests, you only go through one tank of fuel and then call your results good. No, when you're doing tests, you have to go over thousands of miles through several tanks of fuel and average your results. That's the proper way to obtain data. Okay, doing a one data test run is not good enough. I limited myself to 3 runs per test condition. I recorded the volume of fuel used, and as you can see, I weighed it out. The load by the kilowatt meter, the time of the run, HHO, whether it's on, and if it's on, what the volume is, the test iteration, and now a new column, which is very, very important, the exhaust gas temperature. First run, standard, no HHO, just my load board on at 300 watts, okay? And I ran my times. These times, 850, 851, 852. 2-second delta over the 3 runs. The second test, I ran about 2 liters a minute of HHO. The third test, I ran about 0.8 liters. And the fourth test, I ran at about 0.3 liters per minute. What I want to show you here, this is important. So I just introduced the HHO and did not change the fuel to air ratio. Look at the exhaust temperature with no HHO. Oh, about 315, well, average, what is that, 318 or something like that, somewhere in there, okay? Then I put in 2 liters a minute. Look what happens to my EGTs. 303, 307, 308. At 0.8 liters per minute, 311, 313, 311. At 0.3, 316, 316, 317. If you work your way from the least amount of HHO up to the most amount of HHO, as you add more HHO, look what happens. The EGTs go down, go down, go down. Now, the EGTs, these are really low numbers. Man, smack, you're running rich. First thing I want to explain to you, these are not actual EGT numbers. They are reference EGT numbers. And the reason why is because I do not have an EGT gauge drilled and tapped into my exhaust manifold. Okay, what I did, and you saw it in the videos, okay, see that little dot? There's a little dot right there. That little dot marks the place where I measured my EGTs on every run. Same, I took the laser pointer, okay, and I pointed it right at that dot and made my measurements. Now, as I showed you before, as you increase the hydroxy input into the carburetor, your EGTs drop. Now, NOx emissions relate directly to combustion temperature. The higher the combustion temperature, the higher the NOx emissions, okay? So, right off the bat, without an air-fuel ratio adjustment, with just introducing hydroxy into the intake of the internal combustion engine, you instantly begin to decrease your exhaust gas temperatures. NOx is created from the nitrogen in the air and the oxygen at certain combustion temperatures. And the higher that temperature is, the more NOx is created. Without air-fuel ratio adjustments, you are already reducing emissions. These relative EGT numbers are proof that HHO reduces combustion temperature, which helps reduce NOx. NOx is the only emission from an internal combustion engine that the Earth environment is not handled to absorb. They cannot be easily removed by normal environmental processes. The other emissions that are produced can be absorbed by the environment and be reconstituted or recycled, but not NOx. So, of all the emissions parameters, I believe that NOx was the one that was most important to track, and fortunately, because it's related to EGTs, the most easy to track. That's what makes HHO the clear winner. Now let's look at the times. Now the times, very important to note. People have said, well, I hooked an HHO generator up to my vehicle and I didn't see any savings. Well, guess what? I am going to agree with you. You hooked an HHO up to your car. You did not put, if you had a carburetor, any kind of jets or air-fuel ratio control, and you did not see any change in fuel consumption. That would be correct. You must tune your engine. You can't just throw this stuff on and expect it to work. You must tune, and this next set of tests will demonstrate that fact. But look here, what most people have done, what many people have done, and as a result of doing so have given up on trying to implement HHO technology. With no HHO, we're running like 850, 851, 852 seconds on 200 milliliters of fuel. Let's go from the lowest amount of HHO to the highest. Again, 849, 851, 852, then up to 0.8 liters a minute, 846, 856. I had one here at 905. Another run, 841, 842, 849. If you look basically here, not a lot of change in time. I got one fairly decent run at 9 minutes 5 seconds. So what I did with the next test iteration, the same protocol, except this time I installed the carburetor with fuel mixture screw on it. So my first recorded run, I got 8 minutes 31 seconds, 8 minutes 35 seconds, 8 minutes 42 seconds with no hydroxy, with a 300 watt load, and my exhaust temperature right back up there around 320 range. The important thing was getting the exhaust gas temperature readings at that one spot that I showed you back to where it was the first time around. Okay, so I'm back to my baseline again. My best run with no air fuel ratio adjustments. The best run between non-HHO and HHO was 2.63%. That's taking like one individual data point. I took the best one that I had, which was 9 minutes and 5 seconds, and the worst one that I had, which was 8 minutes and 41 seconds. And so the best and worst run, 2.63%. Same thing, no hydroxy. Then I went to 0.4 liters per minute, and about 2 liters a minute, a little over 2 liters a minute, and somewhere around 1.3, 1.4 liters a minute. Same columns. I tried to keep these exhaust gas temperatures, and I did that very simply by I leaned out the fuel mixture to bring that temperature back up to where it's supposed to be. So you can see on all these runs, 320, 319, 320, 322, 321, 320, 321, 320, 318, 320, 317, 318. A solid, consistent exhaust gas temperature. Okay, that was my goal. I didn't go to the lean side. I didn't try to lean it out a little bit like I could. No, I wanted to keep the exhaust gas temperatures exactly as closely as I could the same. Okay, which is kind of hard to do with a fuel mixture screw, but as you can see, it's very possible. You can do that. And so now to the times. Now, on this one, the times are pretty much the same, and the exhaust gas temperatures are not. On this grid, the exhaust gas temperatures are pretty much the same, and the times are not. You can see some longer run times here. Let's go over this data, okay? For my first run, 8 minutes 31, 8 minutes 35, 8 minutes 42, for an average fuel consumption of about 23.29 milliliters per minute on my first run. On my second run with 1.3 liters per minute of HHO, 9 minutes 5 seconds, 9 minutes 2 seconds, 9 minutes 6 seconds, with an average fuel consumption of 22.05 milliliters per minute. My third run at 2.1 liters per minute, 8 minutes 58 seconds, 9 minutes 3 seconds, 9 minutes 2 seconds, for an average fuel consumption of 22.18 milliliters per minute. And on my fourth run, 0.4, which is not very much HHO, 9 minutes 4 seconds, 8 minutes 47 seconds, 8 minutes 43 seconds, for an average fuel consumption of 22.59 milliliters per minute. I took each 3 runs and averaged them. So what I did is I compared non-HHO to the 3 different HHO runs. So for the first set, no HHO compared to 1.4 liter per minute of HHO, with the same exhaust gas temperature, 5.62% increase in economy, decrease in fuel consumption, 5.62%. Between non-HHO run number 1 and HHO run 3, which was about 2.2 liters per minute, 5.00% decrease in fuel consumption. And between non-HHO test number 1 and HHO test number 4, which was about 0.4 liters per minute, 3.10% decrease in fuel consumption. My best run, my best data point at 1.4 liters a minute, 9 minutes 6 seconds, and my worst run, which was with non-HHO at 8 minutes and 31 seconds. Best run delta, 6.82%, which is a 35-second increase in run time between non-HHO and HHO best run. I have demonstrated the importance of maintaining the proper air-fuel ratio. The one thing that I have not done in this test, and I could increase this percentage significantly by adjusting my timing, because this is a small engine, so the ratio between the amount of hydroxy injected and the size of the engine is a lot smaller than on a bigger engine. So this 2 liters a minute has more of an effect on the timing than it would on a 3, 4, or 5 liter car engine. So potentially I could get better numbers by retarding the timing to alleviate some of the detonation effect that's caused by introducing more hydroxy into the combustion chamber. And that I've already proven with the Ranger tests, where I was putting 5, 6, 7 liters per minute into that 4-cylinder engine. Timing is important, but I wanted to leave the timing parameter out of these tests because most of HHO experimenters and people that are trying to implement this on their vehicles are not adjusting their timing.